You're talking from some new place. Is it in Israel? Ah, it's in Croatia. Great, with Marco here as well. Hello, Marco.
So Harish has to go on quarantine when he comes back to Israel. They have to be two weeks in his room, yeah, and not to go out. So
no, he says he doesn't. Maybe Croatia is a green state, so now they now have a list of states. If you return from one of them, you need no quarantine.
Okay.
Yeah, so we are now live on YouTube, and but I see that people are joining, so I'm waiting a little bit with the start. Okay, maybe now it's a good time. So I'm glad to present Bernhard Kroetz from University of Paderborn. And he will tell us about ellipticity and discrete series. Please.
Okay, thank you. I hope you can see the screen. I just so everything is about 3 papers, and oops, this is the main paper. It's a very short paper, 8 pages or so. If you take away the title page and the last page and the introduction, it's even less. So I will talk a little bit mostly about that. And so then in part also on that. And then here, what is relevant is only a small part where I explain things for the group. It's methods. So it will be related to this page 5. And maybe then later, okay, there's not too much. And then there's a third, okay, this is a heavy paper. Whoops, what is this here? Ah, okay. So this is with Patrick, Friedrich, and Henrik, and the other 2 are with Job Kaut and Eric Obdam and Henrik Schlichtkroll. And so they will be also, this paper will be mentioned. So, okay, so let's put this away and start with that. So I prepared the first page. So these are these 2 KKOS, so with Kaut, Obdam, and Schlichtkroll, the first 2 papers, and then the last with Knoop and Delorme and Schlichtkroll. And so it will be something a little bit personal, what I'm saying. So lately I was reading a lot of class field theory. I don't know why, I just got interested in that. It's just so beautiful. And so there's a type of theorem which is easy to state, hard to guess, yeah, not obvious, maybe deep, and very, very difficult to prove. And the prototype of that is the Kronecker-Weber theorem. So every abelian extension of the rationals is contained in a cyclotomic extension. It's a beautiful, easy statement. It's hard to guess, I guess, yeah. And also very difficult to prove. I mean, there's whole books just dedicated to the Kronecker-Weber theorem, which then culminates some sort of in class field theory, which is aesthetics by its own. Okay, this I just wanted to say as the introduction. And so in our field, so how is this? Does it work? Okay. Yeah. So there's a theorem which I think is part to that. It's I call it Harish Chandras theorem. Of course, there's many, but I mean just this one. So for a real reductive group G, the following are equivalent. Are equivalent. Number 1, G has a compact Cartan. Subgroup, so I skip that. And G admits discrete series. Yeah, very easy to state. Yeah, totally non-obvious, absolutely non-obvious, and very, very difficult to prove. So that's personally my favorite theorem of Harish Chandra. Of course, there's the Plunger Theorem. So of course, so he proved much more. So let's see, so I want to talk about this theorem and how to prove it. And so there's a couple of remarks. Of course, I mean, Harish Chandra proved much more. Much or whatever. So more. So he gave a classification in terms of parameters. And what he used was, so this was character theory, orbital integrals related to that, and maybe cusp forms, something he learned from Langlands. Maybe coming back to this, what I wanted to say, I mean, I always wondered, yes, 30 years ago when I started learning the subject, how can I see this for SL2C, C being the complex numbers? You know, is there some simple proof and so on? And then I wondered, and I could never see this, you know, straight away. And so then there's, of course, the Lorentzian groups, SO1, n, which have discrete series precisely when n is even. And so I talk to people who only do rank 1 all their life and say, you know, can you explain me why the Lorentzian groups, I mean, have discrete series only if n is even? Nobody could give me an explanation for that. They all say, oh, it's Harish Chandra. Okay, that's not the answer. Yeah, so it's like, that's not.
So stand over there and tell me.
What?
Bob,
excuse me.
There's nothing there.
I don't hear anything. Is there any questions? Bob said, okay, yeah, whatever, we will see. So, so then this other thing, what I wanted to mention, I mean, as a remark B, I mean, this implication 1 to 2, I mean, so compact Cartan, I mean, some sort of is often called construction of discrete series, the construction or the existence. So out of this data that you have, this geometric data for compact Cartan, I mean, you want to do that. And so here you have to mention a few people. I mean, so first of all, Wilfried Schmidt. So this was a construction using D-bar cohomology. So in his beautiful thesis. And then there was a construction by Attia Schmidt. And this was with index theory. And then there was another construction, so more general, I mean, which I Flensted Jensen, so for symmetric spaces. So this is more general, so symmetric spaces. But as you might know, I'm interested in even a much more general context of real spherical spaces. And I often looked at Flensted Jensen and tried to see, I mean, whether one could save some parts of what he did, but that's not possible. There is simply no concept of duality for a real spherical space. And so all this, what you know, doesn't work. I mean, there is no, I mean, character theory for homogeneous spaces is not a good thing to do. Orbital integrals is not a good thing to do, I think. And cusp forms is also not really working out. So you have to get new arguments. And in this, in general, I mean, some sort of this was provided. I mean, this existence out of a compact torus in a more general of real spherical spaces. I mean, so we did this in this third large paper. Okay. So of course you might ask, you know, could we get a parametrization of discrete series in general? And I think it's not possible. I mean, there was some attempt, I mean, I think partly successful by Oshima Matsuki. But also for symmetric spaces, I mean, the parametrization problem is a very difficult one. So, okay. So I want to explain now the statement, I mean, for real spherical spaces. So what is this analog of Harish-Chandra theorem? So you basically attach to your real reductive group a homogeneous space, G mod H, H being an algebraic subgroup, as a real algebraic subgroup. And so that's called, I mean, real spherical R dot S. So the easiest thing is to say there exists a minimal parabolic subgroup P of G such that pH in G is open.
Bernhard, I apologize. I have a small technical request.
Yes.
I think you can enlarge the whiteboard. There are arrows at the top that allow you to shrink the sides, the things on the sides.
So for me, the arrows on the top.
Yes, yes, yes. Here, a little bit to the right, a little bit to the right.
No, there's
yes.
no.
There is a very small arrow. Maybe if you press it, yes, and another one like this on the left, on the other side.
Okay, but this I need. I mean,
this you need. Fine, fine, fine.
But
fine, thank you.
One I can. In this, on the right column, I need this for the Zoom because I need to see people asking questions.
I see. Fine. I apologize.
Okay, so this is the shortest definition of real spherical. So all symmetric spaces are of this type. This is an enormous class, which you can classify for H reductive, but in general, of course not. So this is the framework I'm interested in. And so then H perp is well, the fiber at the cotangent space, G times HH. So G is, of course, here always the Lie algebra of G. And then, so we had the following conjecture in one of our papers. So, and the equivalent are, the following are equivalent. So, the interior int, so of H perp of the elliptic elements is non-empty. And the second thing is L2 of Z has discrete series. So maybe I should request here unimodular. So in order to speak of an honest L2 space, there's other variants of that. So, but if there's discrete series, so H has to be reductive and it has to be co-compact and it's normalized. So this is known. It's a theorem of Friedrich and mine. Okay, so how does this relate now? I mean, to the group case, I mean, what I wrote down. So you view G under its both-sided symmetries as a symmetric space. Yeah, so it's geometrically, I mean, the group acts on itself by left and right, and then you have here diagonal subgroup, and this is the diagonal subgroup is H. And then, of course, I mean, the Lie algebra is the diagonal subalgebra inside G times G. And H perp, okay, so what's orthogonal to the diagonal is the anti-diagonal of G. And of course, I mean, this is, it's X minus X we identify with G. So H perp elliptic elements correspond to elliptic elements in G. And if you have, I mean, elliptic elements with non-empty interior, this just means there is a compact Cartan subalgebra. Okay, so that's the statement for real spherical spaces. And this one direction of this theorem, so we proved, I mean, this existence part, if there is enough elliptic elements, then there is discrete series. So this was a consequence of this big work on the Bernstein decomposition, which is the basic decomposition of the L2 space into the various different series coming from the geometry of the compactification. Okay, so now I would like to talk about what's behind that and what's the central tool. And so I need a little bit of terminology. So this is standard for this minimal parabolic. So it's a Langland's decomposition. And we take here maximal torus. Okay. So now I define a Cartan subalgebra. I call it C for Cartan. A is the Lie algebra. The split part is A plus T. So this is the Cartan subalgebra. And with that comes the big Y group, WC. And so, of course, it's a thing has real and compact parts. I mean, some sort of the roots typically are not real valued, but you take the real form. I mean, some sort of all roots, we call it CR, is A plus IT. So this is the real form of the complex Cartan. And it has the property, I mean, some sort of that all roots are here real valued. And this is where the root system actually lives. So this is V star stable. So this is the Cartan. Okay, so now if you've got an irreducible Harish-Chandra module, then you attach to it, I mean, so-called infinitesimal characters, so by Schur's lemma. So this is the center of the universal enveloping algebra. And by the Harish-Chandra isomorphism, you attach to that an element, I mean, a Y group orbit, WC lambda, maybe lambda V if you wish. I mean, this is an element in the orbit space. Okay, and this is what's called the infinitesimal character. And so the basic classification of Harish-Chandra module is, so the fibers of this map, I mean, it's to any infinitesimal character, there's only finitely many irreducible representations. So, and then there's a theorem here. So, and this is this work on the infinitesimal characters on discrete series. And it says there exists a rational lattice, I mean, rational with respect to Chevalier basis. Lattice is explicit, you can do WC invariant. Let's call it lambda set, and it's contained in CR star. So it's a real lattice, rational, so multiples, such that, let's get a new page, such that for all discrete series, V of L2Z, for all, you have that the infinitesimal character lies in this lattice. So we were very much interested in this type of a theorem because this was motivated by Sakellarides and Venkatesh in their approach to the Plunger formula for p-adic wavefront spaces. And so this implies a so-called spectral gap theorem. And this is the black box, I mean, which allows you to do Plunger theory. So this was just the motivational thing. And so the question, I mean, back then was posed to us by Patrick Delorme. Okay, so.
Bernhard, lattice means a rational form or actually a Z lattice?
No, a C lattice, I mean, integer lattice. I mean, so basically, so you have the weight lattice, and this means an integer multiple of this lattice is in the weight lattice.
Thank you.
N times lambda set, I mean, so I write it down, N times. So rational, so this number you can write down is contained in the weight or root lattice. One can say, of course, much more. This infinitesimal characters, I mean, so we don't take account here sphericity. There's another Harish-Chandra homomorphism. It's the Knoop homomorphism. It is, I could say a lot of things more, but it's not needed, I mean, at this point. So I want to explain this for the group, the heuristics. How do you see, I mean, for a group out of thin air that the parameters of the discrete series are integral in some sense? Okay, so for the group, and this is actually what was the basic idea in the start. So you can take G as SL2R, doesn't matter. And you take a discrete series for G. So now you do something what you typically don't do, because you all believe in Langdon's classification, and this is somehow, I mean, some sort of which dominates the heads. So you do something else. I mean, you look for principal series cover. They also exist of such a discrete series. So they exist by Castleman's embedding theorem, which you just dualize. So you look at the principal series cover. Okay, so what is this? This is related to asymptotics. Every principal series cover is related to asymptotics. So let me just explain that. So you take a V in V, and then you take the contragradient Harish-Chandra module, so V tilde, and then you construct matrix coefficient, which I denote MVV tilde of G, is matrix coefficient. So it's dual vector applied to GV. Okay, good. And so if we have that, then so you can see, I mean, such a principal series cover, it doesn't matter which one you've got, shows, I mean, there is exists matrix coefficients with asymptotic on A, say A to the lambda plus rho, say A is now in A minus. Yeah, so, and so of course here you have G is K, A minus K, so negative chamber. So whenever you have such a principal series cover, then you find such things. It's actually better to say, I mean, to look for V in V infinity. Yeah, it's better to do this. So doing calculations with K finite vectors is not good. So you take here cutoff functions. This is a direct approximation. And this is explained, I mean, in this introduction of the second paper. So this is in this intro. Okay, so suppose we have that, and well, I mean, there's intertwining operators between principal series. So pi lambda epsilon, and then there's here an intertwiner, and it goes to pi minus lambda epsilon. So this is I, an intertwiner. And this is here goes to. So if this intertwiner would be invertible, yeah, so if I is invertible, then I would also get an arrow here and a quotient if I is invertible. But then by the principle what I have here, then I have another principal series cover, and then I get an asymptotics for the other one, for minus lambda, which would be a to the minus lambda plus rho, right? But you have discrete series, yeah, and discrete series you can measure in the KAK decomposition, and you write down, you know, your favorite Jacobian, and you see this is not possible. This means the intertwiner is not invertible, but intertwining operators is something basic. I mean, they factor in rank 1 intertwiners. This is the Gindekin-Kapelewicz formula, more or less. And so this cannot happen. So, and this means, means the intertwiner is not invertible. And then you basically know that then lambda of alpha check has to be an integer. So there's only one root. Okay, so this idea, I mean, it is explained in the introduction, and then you have to prove something on Y groups. And maybe, I mean, for the group, I mean, it's 5 pages. It's not more. So this is what it boils down to see the statement. I mean, that infinitesimal characters of discrete series are real and integral in some sense. So it's all in the paper. But what I want to say, this is a very soft proof.
Bernhard, can I just ask, is it a computational proof with intertwining operators or more abstract?
No, I mean, no, you know, basically, I mean, some sort of just what the properties of intertwining operators. So this is rank 1 intertwiners. This is what enters here. And this you can analyze. I mean, Birgit is here. I mean, some sort of, it's, yeah, an interesting paper. I mean, the Spee-Wogan paper, I mean, on irreducibility of principal series. So you just need the rank 1 thing. Yeah, it's a fun paper. I mean, I like this paper of Birgit. Actually, I was thinking of writing another proof of it, at least for rank 1. Whatever. So let's say here Spee-Wogan. So this is also, it's an ACTA paper on the irreducibility of principal series. Okay, but I think it goes also a little bit easier. Yeah, as in this paper of those. Okay, so next page. So now we saw, I mean, some sort of that the parameter. So this is the tool what we use, yeah. So what is harder to show, much harder, is that the parameters are non-singular. So this means the stabilizer of the Y group is trivial. This is what Harish Chandras showed. Here I don't know an elementary approach. So I tried very hard to see that. But this seems to be, yeah, a little bit out of reach, Okay, so now we basically this short paper. I mean, some sort of, this is about. I mean, there exists a discrete series. So this is the remaining part, And so this is just for the group. And so you want to see there exists a compact Cartan. Okay. And so I was interested in such a proof or a new concept because I wanted to have methods, I mean, which are deformable to the real spherical situation. So what I present here, I think has the potential to do that. So it has the potential to generalize. So what I can say for certain, I mean, that it works for symmetric spaces. But this is, of course, not enough, yeah. But so this takes away the Japanese work, yeah, of Oshima and Matsuki. I mean, so this is what it is. Okay. So in general, I mean, some sort of, so what we know, I mean, some sort of V is the discrete series. I mean, some sort of is a unitarizable, irreducible Harish-Chandra module. So this is what we have with real infinitesimal character. So this means this lambda V is so this representative is in CR star. So more you don't need to know. Okay, and so well, if you have, I mean, if it's unitarizable, I mean, then the contragradient is isomorphic to its complex conjugate. And this means that the chi of V bar is minus chi of V. And if you translate this, then this means there exists an element in the Y group such that W of lambda bar is minus lambda. And so we recall, I mean, this real form CR is A plus IT. So minus the conjugation, yeah, equals the Cartan involution on CR. So, so that's what this identity, what we've got. Now I need a little bit of terminology. So I introduce what's called extended Y group. So what we call extended Y group. So WC extended. And what is this? Well, this is just WC. I mean, if theta is in the Y group, and otherwise it's this extension. Okay. And if we look now back, and so I call a parameter lambda, I call strongly regular if the stabilizer in WC extended is trivial. Okay. So now this condition, what we had, I mean, lambda, W lambda bar is minus lambda. You can also rewrite that W lambda equals theta lambda. And W times theta is in the extended Y group. So this means if I have only one representation with a strongly regular infinitesimal character, then theta lies in the Y group. So consequence. If there exists only one representation in the discrete series with strongly regular infinitesimal character, then theta, if you want like this, lies in the Y group. Okay, but this is now a condition which is which people studied. So I learned it in hindsight. That in the American school, there's paper by Adams. But okay, this is what you discover by yourself too. This is then the following are equivalent. This is not very difficult. It's in this short paper, 1 page at most. Theta is in the Y group, is equivalent to theta being inner, an inner automorphism, and being equivalent, K has full rank. Oops. Plus. Third thing, K has full rank. So this is not very difficult. So for instance, if theta is inner, then theta is given by some at G, so on the Lie algebra. So for some G, actually some elliptic element, semi-simple element. Yeah, but then you see, G theta is, well, the centralizer in G of such this element. Yeah, but this G was semi-simple, so this contains, this is on the one hand side, this is K, but on the other hand, because G was semi-simple, this must contain a Cartan, so it has full rank. Rank of K or KC, rank of K is rank of G. More or less, something like that. All right. So this is this very soft thing, so that this infinitesimal character is just real, tells you, well, so there's compact Cartan provided you find one, yeah, which is strongly regular. Okay, so I came further than I expected, so it went further. Okay, so now we remain, to show, some sort of to construct out of a discrete series with infinitesimal character, say lambda, another one with strongly regular infinitesimal character. Okay, so this looks at you and okay, the literature is, but that's in essence, so you have to do it in a smart way. Some sort of the Zuckerman translation principle. So you tensor with finite dimensional representation. Okay, and so then there's a way, some sort of to create then out of discrete series, one with a strongly regular infinitesimal character. So what we seek is a finite dimensional representation F. And so then we look at our Harish Chandra module V tensor, and and inside this we look for some U, yeah, which has to satisfy two things. Some should have some strongly regular infinitesimal character. and should lie in the discrete series. So there's two things which you have to manage here. So, and in some sense, I mean, this is achieved in 2 steps. Yeah, I mean, okay. So now I'm basically a little bit embarrassed because I didn't think that I come so far in this talk, so it went faster than I thought. So now I have to improvise. Okay, so but I wanted to, so this in general, I mean, so what I need to explain is, I mean, this infinitesimal character chi v, I mean, it's basically a Y group orbit, something like that. And how this Y group orbit is related, I mean, some sort of to the asymptotic expansion. So you have here MVV tilde of A, and so this should be, roughly speaking, so there should be some leading exponents. And then you have the root lattice, say alpha in N0. This is the root system with respect to A. And then we have here A rho plus lambda plus alpha, and then here P lambda alpha. Okay. So that's roughly how it looks like. And this P lambda alpha of A is a polynomial in log A. If the parameter was regular, these polynomials are just numbers. And so what is important is the relation, I mean, to the infinitesimal character, so that EV is contained in this Y group orbit restricted to A. And here A is in A minus, maybe in the interior, so A minus or whatever, it doesn't matter. Okay, and you can read off discrete series. I mean, some sort of, you can read off, this is very basic. I mean, I think this is one of the, another central thing in the theory of Harish-Chandra modules is the existence of these expansions. And me and my co-workers, I mean, in order to get this right, and in the context of complete generality for real spherical spaces, took me about 2 years to understand and get this formula completely in this generality. But this is something very basic. I mean, some sort of, this is basic for all Harish-Chandra modules and has nothing to do with discrete series. And now, I mean, once you know that, okay, so maybe one should mention here also the work of Kasselman and Milicic, I mean, some sort of in Duke, who basically wrote it up, I mean, in a more modern way, and this is the way how it went into the textbooks. Okay, and so what is then the discrete? So that V is in the discrete series, yeah, can be read off from this exponents. And notice, I mean, some sort of this exponents, I mean, some sort of, so this is actually, let me just take it away. So we need to löschen here. Okay, so I need to write. So I take here the real form, it's the real part here. Take here. So it can be read off here. Yeah. So this is completely opposite. I mean, some sort of this, this is with respect to the split Cartan. It has nothing to do, I mean, some sort of with the fundamental Cartan. And so the discrete series condition, they sit somewhere completely else. I mean, on the, so here, the emphasis is on the split Cartan. Okay, so you, when we look back here, so A was in A minus, A to the row is good. This is already in L2 plus epsilon. This means lambda has to be positive on the Weil chamber. So this means, oops, can be rid of a more precision. So real part of this here is in the interior of the dual Weil chamber. So in other words, this is the sum of all positive roots in A. So that's this. So this is the big Weil chamber. Yeah. So so typically this is the Weil chamber. So this is A. And then this is the dual one. Yeah. And there can be many elements in a Y group orbit here, which can be exponents. And it's, for instance, an open problem for discrete series, and nobody knows that, as far as I understand, is to say which, even if you know the parametrization and everything, you know, what are the exponents of a discrete series, or more general, I mean, of a derived functor module. So the link of the work of Vogel to harmonic analysis is actually not established, in the sense, I mean, some sort of that there is, of course, other data. I mean, to any Harish-Chandra module are a set of exponents, and you need to say which ones occur. And it's typically not that the nice ones occur, it's that the bad ones occur. All right. So that's what we've got. So, and so we have now one, I mean, so the situation is, let me make this picture here, so of C2. Maybe here is our lambda, which is not regular, not strongly regular. Yeah. So we don't know. I mean, it could be. I mean, some sort of, in some sense, I mean, the lattice. I mean, it might be only half integral. Yeah. If the thing would be far enough out, then you could tensor with a finite dimensional representation, and you would still stay there. But if the parameter would be there, and I come with a finite dimensional representation, then so it's not true. So that also V tensor F, yeah, is always in L2 of G. Yeah, so this is this you can forget. So first, I mean, some sort of we want to push in the direction of lambda. Okay, so we. Yeah, so we know that n times lambda is integral. Let's call this mu. Okay, and or maybe mu not. And mu is then basically the dominant element. And F is the finite dimensional representation, F mu, with highest weight mu. So here this we can do, I mean, some sort of, we basically now push, I mean, with our finite dimensional representation here. And now you would like to see, I mean, some sort of, oops, next slide. So what is the asymptotics of V tensor F? And this asymptotics, I mean, some sort of, you can also see, I mean, some sort of in what's called the Kasselmann-Jacquet module or functor. So this is a functor J. So this goes from the category of Harish-Chandra modules to whatever generalized category O, doubly generalized. I mean, some sort of, so category O typically, I mean, some sort of has weight decompositions being semi-simple with respect to the Cartan. So here you have to allow, I mean, generalized eigenspaces, and then of course it's not the Borel, it's a minimal parabolic, whatever. But this V, I think, goes over to J of V, and maybe it's this limit V mod NKV. And what is this? This N is the Lie algebra of N, the Iwasawa N. Yeah. Of P is MAN. Okay, and the weights here basically are those, I mean, some sort of relate to the exponents. And the point then is, so for a finite dimensional representation, J of F is F, this is easy, and this commutes. So this is not, I mean, this is J of the tensor F. Well, but this is tensoring finite dimensionals in category O here. And this is easy. Yeah, so then you can locate, I mean, some sort of an exponent or an infinitesimal character, some sort of which is further out. So this allows us in this picture to push in this direction. Yeah. So now we are far out. And if I'm far out, yeah, then I can also move a little bit left, and I can move a little bit in this direction, yeah, and I still stay, yeah. So this basically gives still the infinitesimal character is then no longer lambda, but it's n plus 1 times lambda. It's large, but still singular. This was lambda, and then we pushed here with lambda plus mu, and mu was n times lambda, so this is n plus 1 times lambda. And now I'm in a good situation, because if the infinitesimal character is large, then I can come with small representations. So small f, so means highest weight is small. So side 10 plus. Okay, so small then, I mean some sort of this new translated one. So let's call it V tilde. So, no, that's not good. So what we basically found now, U is in V tensor F. So this was then a discrete series with infinitesimal character n plus 1 times lambda. And now this U we can now translate with another F, maybe F2 or so, F2 small. And now I can change it as much as I want. If I have pushed it out far enough, I mean some sort of, I can make then lambda regular. I can move the lambda from the wall, yeah? So I move it here, it's all fine, yeah? So, and then you are done, more or less. Okay, finished. Okay, so that's not how we wrote it in the paper, because so we used things which are easily to cite in the literature. There is a paper by Hecht and Schmid. So this was, I think it's a beautiful paper. It was the solution of the Osborn conjecture. Yeah. And this was the first time, I mean, some sort of this n-homology business was written up in a systematic way. Here's another name. Yeah, and so here this is more like in terms of homology of n of v, but this is the same thing. The n homology of a Harish-Chandra module is strongly related to this leading exponents. And so that's what we use here. And so Hecht and Schmid wrote things up in sufficient generality. I mean, this here is not a module for A, but also for the center of M plus A. And that was needed. Otherwise, you would have to write too much. And I think for this generalized category, oh, I mean, the literature is not so good. And so that's why we wrote it more in this language. Okay, folks, I think this is what I wanted to say. So it basically, I mean, to wrap it up, there was two things. So there was discrete series with strongly regular. This is the first thing, I mean, infinitesimal character in some sense. Some sort of implies, I mean, that a very special element, theta, is in the Y group. And then this, in turn, I mean, some sort of implied existence of elliptic elements. And then this was one thing what we did. I mean, some sort of this. This is a procedure which is for symmetric space. It runs right through. And then the other thing is, I mean, some sort of is to have a translation principle. And in general, I mean, some sort of what we look for or what we hope to establish is a translation principle, I mean, some sort of for spherical or distinguished representation. So this is what we want. So we want a version of the Zuckerman translation principle in the distinguished category. And so for symmetric, I mean, this goes rather well. I mean, some sort of because the finite dimensional spherical representations are fairly well understood. But in general, I mean, some sort of there's some obstacles here. Okay, but this is basically a two-step program. The one is basically invariant theory and constructing elliptic elements, and the other one is more representation theoretic. So for the group, I mean, things are very simple. And so this, what I want to say, I mean, in the end, I mean, this Harish-Chandras theorem, I mean, can be proved now in 15 pages easily, or 10 to 15 pages, without using anything more than the asymptotics of matrix coefficient. And if you want, I mean, this Zuckerman translation principle, but if you look at the paper of Zuckerman, it's just the first part what you need. It's another 3 pages and it's very elementary. It just multiplies characters. So I think it's a step forward in terms of understanding. I don't know if you understand them more, but I think it's very soft and it has the chance to generalize. Okay, thank you.
Thank you. Questions, please.
Yeah, can I ask one thing, just a clarification?
Yes.
Can you explain that theta, what was it? It was just some automorphism of G that when you form that semi-direct product with the complex while group?
Okay, let's see. Okay, theta is of course an automorphism of the root system, right? I don't hear you. You have to put on your microphones and go.
Okay, no. So it's not an automorphism of the Lie algebra G, or
no, it is. It's the Cartan involution. I mean,
okay. It's just a Cartan involution.
It's just the Cartan involution.
Okay. Yeah,
Oh,
I thought
sorry,
it was the
I didn't say
notation
this.
is theta. Okay. So you look at the special case where theta is actually inner.
Yeah, I mean, this is what it is. I mean, some sort of, if you find an element which is strongly regular, then this means, so theta w, so this means theta w fixes lambda, and this means it has to be 1. Yeah, so this means w, I mean, theta lies in the Y group.
Okay.
But it could be, I mean, that that all parameters a priori of discrete series are singular, then you don't get this condition. Yeah.
Okay.
Only,
Okay. Thank you.
yes.
More questions, please? Okay, then I have a question. So you say that the translation principle works for symmetric spaces?
Yes.
Can you say a little bit more about this? How does it work?
Okay, so yeah. I mean, okay, so now we have an extra datum. So you have a functional eta which is H invariant. Yeah. And so instead of MV V tilde on the group, you look at MV eta on the homogeneous space. Of course, Harish would say I write the H on the wrong side. Yeah, of course, I'm doing it wrongly. Yeah, so the right way to do is of course this. I don't have any opinion here. So in any case, so this MV eta, and so as I said, I mean some sort of we have a so and now, I mean, what you do is you multiply matrix coefficients. Yeah. So now you also want that F is H spherical. Okay. So it has a highest weight mu, and so maybe a spherical vector nu. H invariant. And what you essentially do, I mean, you have here matrix coefficient MV, and then you multiply it with a matrix coefficient, say U is in F, and then M, and then this gives you another C infinity function on G mod H. And so it has asymptotic expansion. So, okay. Now, I mean, you want to push in the direction of a leading exponent. And so in some sense, I mean, in this thing, I mean, some sort of in V tensor F or V, so here, so that's what it is. Now you need to locate a spherical submodule. So what we did before, I mean, some sort of, we took our lambda, and the lambda is the correct one, and then you take n times lambda to be integral, and then we called it mu, or mu naught or so. Yeah. And now you need to see that the dominant one, I mean, some sort of mu is the dominant element in the Y group orbit. So if it would be like that, I mean that F mu is spherical, then you're done. So, but it's not clear, you know, some sort of, in general, I think is also not true. It's not so simple. Yeah. So you need to see, I mean, the direction in which you push, yeah, belongs to a finite dimensional representation when you restrict this invariant function of some sort of this A weights decomposition. I mean, some sort of so now, okay, this is a new alpha. So this is the A weight decomposition of the spherical vector in this finite dimensional representation. So you need to find one, I mean, some sort of, so this 1 alpha, I mean, some sort of the direction what you want to push is non-zero. That's somehow the point. Yeah. Okay, I mean, what was this? Oops. I don't know. Somehow something is lost now. I forgot. Okay, but I mean, you need to make sure. I mean, some sort of the direction you want to translate belongs to a finite dimensional spherical representation, and this is the issue here. And for symmetric spaces, two Y groups coincide. I mean, the little Y group and the little Y group, so this of the spherical space is the little Y group of the symmetric space. This is more or less the reason why it works. And if you are not in a wavefront situation, I mean, then these things are different. And so it's at the moment not so clear, I mean, some sort of how this works. Yeah, I mean, it's there's one thing, I mean, some sort of to push with finite dimensional representation, but I mean, nobody ever said anything. I mean, some sort of maybe you take two unitary representation, H1 and Tensor, an irreducible. And so actually you would expect, yeah, so if these are discrete series and I branch them to G, that it contains discrete series of larger infinitesimal character. But in this situation, I mean, nobody could say anything. I mean, some sort of, there is more or less only the paper by Repka. I mean, you want to translate in some sense, yeah? So I can ask the following question, yeah? So I take a discrete series, H, and I take another one, I take it itself. And does it contain, so say a discrete series with parameter lambda, I mean, does it contain one with 2 lambda, for instance? I mean, there's much more flexibility, but this type of branching, I mean, is not understood. I mean, some sort of, it's just extremely difficult. So I tried on this. I tried to prove this, but I failed. Yeah, so because the techniques, I mean, so this has closeness issues. I mean, some sort of on operators. I mean, some sort of which are difficult to get your hands on. I just what I wanted to say. I mean, there is not only one way to translate or push. I mean, there should be several ways. I mean, some sort of maybe to construct representations with more regular infinitesimal character.
I see. Thank you very much. Are there any further questions? Okay, if not, then thank you again.
Thanks.
So next week we will have Axel Kleinschmidt, who will tell us about string theory and relation to Fourier coefficients of automorphic forms, in particular minimal and next to minimal automorphic representations.
Okay. Thank you for attending. Yeah.
Thank you for talking. See you everyone next week. Bye.